Good morning, myself I'm R. Akshaya from CSIT branch. Today my Tech Talk concept is power supplies for consumer electronics. Course outcomes: Introduction on consumer electronics, power converter classification, power converter building blocks, important design factors, applications, examples. Introduction: A device used for non-commercial purposes in entertainment, communication, and home offices is called a consumer electronics devices, which incorporates electronic circuits for operation. By this definition, computers, cell phones, mobile devices, light-emitting diodes, lights, TVs, cameras, gaming stations or consoles, and various other home electronics are examples of CEDs. Most CEDs require DC power to drive the electronic circuits. A utility connected house receives a single phase as AC input. This supply can be 230 volts, 50 Hz or 110 volts, 60 Hz depending on geographical location. And AC to DC power supply is used to interface the AC grid input to CED. Inside a CED, there are various analog and digital electronic circuits and integrated circuits to process electronic information. These ICs require dedicated power supplies because the voltage, current and dynamic requirements are different. Therefore, there are multiple DC to DC power supplies known as point of load converters on the IC card or motherboard. With renewable energy becoming popular, DC supply is directly available for use in homes. There is also an effort to standardize DC power distribution and CEDs that work with this standard. A consortium known as Emerge Alliance works with several multinational companies to streamline this effort. And this article, a general overview of power converters used in CEDs is discussed. Basic network theory and control engineering will be used to explain the fundamental operation of a converter and its application. Power converter classification. Based on input-output profile, a power converter or power supply is used to efficiently convert and control power from one voltage, current, frequency level to another. Based on the profiles of input and output voltages, a power converter can be classified into four types. First one, DC to DC converter. Its input and output voltages both are unipolar in nature. Depending on the magnitude of voltages, they are further divided into three types: a step-down or buck type, where the magnitude of the output voltage is smaller than the input voltage, a step up or boost type, where the magnitude of the output voltage is higher than the input voltage, and the up down or buck boost type, where the magnitude of the output voltage can be either smaller or higher than the input voltage. Buck type DC to DC converters are very common in CED applications to power digital ICs inside a CED. Boost type DC to DC converters find applications in universal serial bus, charging ports, sensor power, and powering portable speakers, among others. Similarly, buck boost type DC to DC converters find applications in smart devices, bias supplies, and so on. DC to AC inverter. It has a unipolar input voltage and bipolar periodic AC voltage. They are quite common in uninterrupted power supply design to provide battery backup for grid supply. Solar inverter to interface PV source to grid also belongs to this class of converters. AC to AC converter. Its input and output voltages are both bipolar. In modern applications, AC to AC converters can be realized by cascading an AC to DC converter and DC to AC converter. AC to DC rectifier. It has a bipolar periodic AC input and a unipolar DC output. All types of AC adapters belong to this family of converters. From this classification, it is clear that as far as block level operation is concerned, every converter is a nonlinear block because its output contains a frequency component other than its input frequency. The figure shows the several types of power supplies or power converters used to supply power to the CED. This figure shows the power converters are classified based on input and output voltage profile. The first figure shows the DC-DC. Green has a unipolar input and a unipolar output. B figure shows the DC to AC has a unipolar input and an AC output. The AC to AC has an AC input and an AC output. D figure shows the AC to DC has an AC input and a unipolar output. Isolated versus non-isolated. Sometimes in offline applications, a converter is required to galvanically isolate the utility grid input and the DC output. This is generally achieved by using an isolated DC to DC converter. The basic structure of an isolated DC to DC converter is shown as a figure. It is realized by cascading a DC to AC inverter, a high frequency transformer, and an AC to DC converter. High frequency transformers makes the overall converter design smaller by reducing the transformer size. Isolated DC to DC converters are used to improve safety, enhance noise immunity, and achieve a large step-up or step-down ratio between the input and output. Figure B and C depicts the way an offline isolated converter provides protection against installation failure of equipment. In an isolated DC to DC converter, the transformer provides insulation against direct short to ground. In comparison, a non-isolated DC to DC converter doesn't provide protection against insulation failure. This figure shows there are three pictures and circuits in the given figure. The first figure shows an isolated DC to DC converter. The second figure shows isolated converters provide protection against insulation failure based ground faults. The third figure shows non-isolated DC to DC converters do not provide protection against insulation failure based ground faults. HF, that is high frequency. This figure we have two more circuits, which says the first one says that the basic building blocks of a DC to DC converter, and the second one says the electrical equivalent circuit of a converter. PWM, pulse width modulator. Power converter building blocks. A power converter consists of two major building blocks, a power stage and a control stage. The power stage is responsible for processing the power between the input and the output. The control stage controls the converter parameters. Example, maintains the fixed output voltage if the input voltage varies. The control stage doesn't have any power processing capability and is generally realized using low power electronic circuits. Both mixed signal ICs and fully digital ICs are common in the implementation of the control circuit. There are various sensors that feed the converter voltage or current information into the control unit. Based on this information, the control stage generates a square wave pulse width modulated signal to drive the converter. From a terminal behavior point of view, a converter works like a voltage or current source. The feedback and control implementation decides the source type. If the output voltage of the converter is regulated, the converter behaves like a voltage source. This essentially means that, similar to a voltage source, the output voltage of the converter remains constant irrespective of variation in load current, input voltage and other parameters. Similarly, if the output current of the converter is regulated, the converter behaves like a current source. In this case, the load resistance decides the output voltage. Some important design factors. Output power. The power rating of a converter depends on the load it is designed to support. The overall objective is to reduce cost and improve the efficiency of the converter. When the load current is in the order of tens to hundreds of milliamperes, a similar linear regulator or switch capacitor circuits is preferred. They are mainly used for bias application. However, as the load current level increases beyond a few amperes, a switching converter is the most optimal solution because it provides the best trade-off between efficiency and component count. Here, another factor that affects the power supply design choice is the ratio of input and output voltages. If the input to output ratio is high, even if the load current is low, a switching converter is the most optional solution. This is because a linear regulator with a high input to output ratio, the voltage drop across the semiconductor device is very high, which leads to higher power loss. When the load current is very high, it is advantageous to use multiple parallel modules as shown in figure 6. This type of design leads to better efficiency, energy density and modularity to the power conversion system. This figure shows an example of a controlled buck converter as a current source. The figure A shows the schematic and the figure shows the response of the source to a given reference. In this figure, we can see the network theory rules need to be followed by a DC to DC converter operating as an independent source. The figure B represents paralleling of a DC converters is a very common technique to realize higher power modules. Dynamic and controls. As far as control function is concerned, there are primarily two aspects of power converters used in CADs that are important. Control in the converter output follows a desired input reference signal, and regulation is in that the converter output remains within desired limits with change in input voltage load or other parameters. High switching frequency operation. The switching frequency is the rate at which the switches of the converter are turned on and off in a second. In modern designs, the switches of the converter are operated at 10 seconds of kilohertz to several megahertz. The advantage of higher switching frequency operation of a converter are the following. It leads to smaller magnetic and filter capacitor size. This results in higher power processing density of the converter. This figure shows the control of the output voltage using a reference signal, and the B shows the regulation of a converter output with a change in load current. The figure shows a comparison of efficiency and the basic technique used in LED dimming circuit. The converter can be designed to have faster dynamic response. The drawbacks of increasing the switching frequency are the following. It leads to higher power loss in the switches, design, printed circuit board layout, and the electromagnetic interferable become critical. The selection of switching frequency depends on switch type. At higher switching frequency, GaN-based converters have a distinct efficiency advantage due to a very high speed of operation inherent to GaN-based MOSFETs. Their packaging plays an important role in harnessing this feature. Applications example LED dimming circuit as follows: battery charges. The basic control of an optimal battery charger and an experimental battery charge profile of 36 12 volts lead acid battery. Thank you.